Tonight, I want to take you somewhere quiet, somewhere far from the familiar blue of our own sky, to a place where the colour blue takes on an entirely different meaning. A place where storms rage for centuries, where winds move faster than the speed of sound, and where, perhaps most remarkably, it rains diamonds. Yes, you heard that correctly. Tonight, we're going to drift together through the outer reaches of our solar system to the ice giant Neptune, where the impossible becomes possible, where carbon transforms under pressures we can barely imagine into crystals that would be priceless here on Earth, yet fall like rain through alien atmospheres. Before we begin this journey together, I want you to find a comfortable position. Perhaps you're already lying down, maybe you're settling in for the night, or perhaps you're simply seeking a moment of peace in your day. Whatever brought you here, you're welcome. Take a deep breath with me. Feel the weight of your body settling, the gentle rhythm of your breathing becoming steady and calm. We have time tonight. There's no rush. The cosmos has been waiting billions of years to share this story with you, and it can wait a few moments more while you get comfortable. As we prepare to explore this cosmic mystery together, I'm curious about you. Where are you listening from tonight? Is it late where you are, with stars perhaps visible outside your window? Or is it afternoon, with sunlight still warming your room? Whatever time zone you're in, whatever corner of our small blue world you call home, you're part of this story. And if you find comfort in these cosmic wanderings, if the gentle rhythm of these words helps you drift towards sleep, while your mind explores the universe, consider subscribing to join me on more of these peaceful journeys through space. Like this video if it brings you peace, and remember, there's always another mystery waiting for us among the stars. Now, let's widen our gaze together and consider the scale of what we're about to explore. If you compressed the entire history of the cosmos into a single day, starting at midnight with the Big Bang, our entire human story would occupy only the last few seconds before the clock strikes midnight again. The formation of our solar system would happen around 3:40 in the afternoon of this cosmic day. Neptune, that distant blue world we're visiting tonight, would have formed just minutes after that in cosmic time, yet it's been spinning in the cold darkness for over 4 billion years by our reckoning. In all that time, through all those patient orbits around our sun, diamonds have been falling through its atmosphere like rain. It's a question that might seem too fanciful at first, almost like something from a fairy tale or a science fiction story. How could it possibly rain diamonds anywhere? And yet, this isn't fantasy. It's physics. It's chemistry. It's the patient work of pressure and time and temperature, creating conditions so extreme that the ordinary rules we know here on Earth bend and reshape themselves into something extraordinary. The carbon that makes up the graphite in your pencil, the carbon that forms the backbone of every living thing on Earth, that same element becomes something magical in the deep atmosphere of Neptune, not through any mystical process, but through the quiet, relentless pressure of a world 80 times more massive than Earth. What if the quiet pressure of distant worlds is also a mirror for the quiet pressures within us? What if the transformation of simple carbon into crystalline perfection under the weight of an alien atmosphere tells us something about transformation itself, about how pressure and time can create beauty from the most common elements? These are the kinds of questions we'll explore together tonight, not with urgency or alarm, but with the same patience that the universe itself employs in its grandest processes. Consider for a moment how we even know about Neptune at all. It's so far away that light from the sun takes over 4 hours to reach it. If you could travel at the speed of a commercial airliner, it would take over 300 years to get there. And yet, we know it's there. We've seen it through telescopes. We've sent a spacecraft past it once, just once. In 1989, when Voyager 2 made its lonely journey through the outer solar system. That single flyby gave us most of what we know about this distant world, and in the decades since, we've been piecing together the story of what happens in its deep, cold, compressed atmosphere. The story begins with methane, a simple molecule made of 1 carbon atom and 4 hydrogen atoms. Here on Earth, we know methane as natural gas, the blue flame on your stove, the bubbles that rise from swamps and marshes. But on Neptune, methane is part of the atmosphere itself, drifting through clouds of hydrogen and helium, slowly sinking deeper and deeper into the planet's interior. As it sinks, the pressure grows. First, it's like being at the bottom of Earth's ocean. Then it's like being under a mountain. then it's like nothing we have on Earth at all. Pressure so intense that the very bonds between atoms begin to behave differently. At these pressures, something remarkable happens. The methane molecules begin to break apart. Not violently, not suddenly, but slowly, inevitably, like ice melting in reverse. The hydrogen atoms drift away, joining the swirling atmosphere, while the carbon atoms, suddenly free, begin to find each other. Under pressures 1,000,000 times greater than what we experience at Earth's surface, these carbon atoms have no choice but to arrange themselves in the most stable configuration possible, and that configuration, at these pressures and temperatures, is diamond. Imagine it with me, deep in Neptune's atmosphere, perhaps a third of the way down. Toward its core, carbon atoms are being squeezed together with such force that they lock into a crystalline lattice, each atom bonded to 4 others in a perfect tetrahedral arrangement. These aren't the diamonds we might imagine from jewelry stores, carefully cut and polished to sparkle in the light. These are raw diamonds, perhaps tiny, perhaps clumped together, perhaps imperfect, but diamonds nonetheless, forming continuously in the crushing darkness and then falling, slowly falling, deeper into the planet. The journey of a diamond on Neptune is nothing like the journey of rain on Earth. Our rain falls for minutes, maybe an hour in a long storm, but a diamond falling through Neptune's dense atmosphere might take thousands of years to sink from its point of formation to wherever it finally comes to rest. It's a rain that never reaches the ground, because there is no ground as we understand it, only denser and denser layers of compressed gas and liquid, gradually transitioning to something that might be solid, but under pressure so extreme that the distinction between solid and liquid begins to lose meaning. This is where our human perspective becomes both humbling and essential. We're used to thinking of diamonds as rare, precious symbols of permanence and value. The largest diamond ever found on Earth, the Cullinan diamond, was about the size of a fist and was considered one of the greatest treasures ever discovered. But on Neptune, diamonds might be as common as raindrops in a thunderstorm. They might accumulate in layers thousands of miles thick. The total amount of diamond on Neptune could exceed the mass of Earth itself. It's a reminder that value, rarity, preciousness, these are concepts that only make sense in context. What is impossibly rare here is mundane there. What we treasure, the universe produces with casual abundance in places we can barely imagine. And yet, for all this abundance, we've never seen these diamonds directly. We can't. Neptune is too far away, its atmosphere too opaque, the diamonds too deep. Everything we know about diamond rain on Neptune comes from inference, from models, from laboratory experiments that try to recreate those alien conditions here on Earth. Scientists have taken methane, subjected it to enormous pressures using diamond anvil cells, devices that can squeeze materials between 2 diamonds, to create pressures approaching those in planetary interiors, and they've watched what happens. They've seen the carbon separate from the hydrogen. They've detected the formation of diamond crystals. They've measured the temperatures and pressures at which it occurs. And all of these experiments point to the same conclusion. Yes, it really does rain diamonds on Neptune. But why Neptune? Why not Jupiter or Saturn, which are even larger? Why not Earth, which also has carbon in its atmosphere? The answer lies in a delicate balance of composition, temperature and pressure. Jupiter and Saturn are too hot. Their massive size creates internal temperatures that would vaporize diamonds before they could form. They're also composed mostly of hydrogen and helium, with much less methane than Neptune. Earth, on the other hand, doesn't have nearly enough pressure. Our atmosphere is a whisper compared to Neptune's crushing depths, and our carbon is busy doing other things, cycling through life and rock and ocean in ways that Neptune's carbon never could. This brings us to one of the most beautiful aspects of planetary science. Every world is unique. Even planets that seem similar from a distance turn out to have their own particular chemistries, their own weather patterns, their own internal processes. Neptune and its twin, Uranus, are both ice giants, both blue-green in colour, both far from the sun. But even they differ in subtle ways that affect how diamonds might form in their atmospheres. Uranus is tilted on its side, rotating like a rolling ball rather than a spinning top. It's slightly less massive than Neptune, slightly cooler, with a different internal heat flow. These differences might mean that diamond rain on Uranus happens at different depths, at different rates, creating different sizes of diamonds. Or perhaps the process is nearly identical on both worlds, and they share this remarkable weather pattern. 2 blue worlds in the outer darkness, quietly raining treasure into their depths. The mathematics of this process are surprisingly elegant. Carbon has a specific density. The surrounding atmosphere has its own density. As diamonds form and begin to fall, they create a kind of circulation pattern. The falling diamonds carry carbon downward, while other materials rise to take their place. It's like a very slow, very strange version of the water cycle on Earth. But instead of water evaporating and condensing, it's carbon crystallizing and sinking. This circulation might play a role in Neptune's internal heat. As diamonds fall and eventually dissolve or settle in the deep interior, they release gravitational potential energy, which becomes heat. This heat then drives convection, which brings more methane into the diamond-forming regions, continuing the cycle. Think about that for a moment. Neptune is still warm, still radiating more heat than it receives from the Sun, 4.5 billion years after its formation. Part of that heat, perhaps a significant part, might come from diamonds falling through its atmosphere. The gentle rain of crystals, each one releasing a tiny amount of energy as it falls, collectively warming the planet from within. It's a heat engine powered by precipitation, but precipitation unlike anything in our earthly experience. The pressure at which diamonds form on Neptune is almost incomprehensible in human terms. We're talking about millions of atmospheres of pressure. To put that in perspective, the pressure at the bottom of the Mariana Trench, the deepest part of Earth's ocean, is about 1,000 atmospheres. The pressure needed to form diamonds on Neptune is 1,000 times greater still. If you could somehow stand at that depth in Neptune's atmosphere, protected by an impossibly strong suit, the pressure would compress your body to a fraction of its normal size. Every atom in your body would be squeezed closer to every other atom. You would, quite literally, become denser. But of course you couldn't stand there, because there's nothing to stand on. At these depths, Neptune isn't really a gas anymore, but it's not quite a liquid or solid either. It's something in between, something we call a supercritical fluid, where the distinction between gas and liquid disappears. It's a state of matter that barely exists on Earth, found only in certain industrial processes or in tiny pockets deep in our planet's crust. On Neptune, it's the norm for thousands of miles of depth. The temperature at these diamond-forming depths is equally extreme, perhaps 5,000 degrees Celsius, as hot as the surface of the Sun. But temperature, like pressure, behaves differently under these conditions. The heat doesn't radiate away as it would in our atmosphere. Instead, it's trapped, compressed, becoming part of the very structure of the matter itself. The diamonds that form at these temperatures aren't the clear, cold crystals we might imagine. They're hot, perhaps glowing with their own light, though that light would be invisible in the utter darkness of Neptune's interior. And what happens to these diamonds as they continue to fall? This is where our understanding becomes less certain, where science gives way to educated speculation. Perhaps they eventually reach a depth where even diamond isn't stable, where the pressure and temperature cause them to transform into some other form of carbon we haven't even discovered yet. Perhaps they accumulate in a layer, a blanket of diamond surrounding Neptune's core. Perhaps they dissolve back into the metallic hydrogen that might exist at the planet's center. We simply don't know, and in that uncertainty there's a kind of beauty, a reminder that even with all our knowledge, all our models and experiments, the universe still holds mysteries. The light from Neptune takes 4 hours to reach us, which means when we look at Neptune through a telescope, we're seeing it as it was 4 hours ago. In a very real sense, we're always looking into the past when we observe the cosmos. The diamond rain that's falling on Neptune right now, at this very moment as you listen to these words, won't be observable by us for another 4 hours, and even then we won't see the diamonds themselves, only the faint blue disk of the planet, a single pixel in most telescopes, holding its secrets close. This temporal displacement adds another layer to our contemplation. While you've been listening to these words, perhaps 10 minutes have passed. In that time, diamonds on Neptune have fallen perhaps a few centimeters through the dense atmosphere. They've been falling since before you started listening, and they'll continue falling long after you've drifted off to sleep. They were falling when you were born, when your parents were born, when humans first looked up at the stars and wondered what they were. They've been falling for millions of years, a constant patient rain in the darkness. The spacecraft that gave us most of our knowledge about Neptune, Voyager 2, is now far beyond the planet heading into interstellar space. It's been travelling for over 45 years, and it will never return. The images it sent back the data it collected during its brief encounter with Neptune, that's all we have from a close perspective. Everything else we've learned has come from telescopes, from computer models, from laboratory experiments. We've had to piece together the story of diamond rain from fragments of evidence, like detectives solving a mystery where the crime scene is 3 billion miles away. In those Voyager images, Neptune appears as a serene blue sphere, with subtle bands of clouds and a few dark spots that are actually massive storms. The Great Dark Spot, a storm the size of Earth, was rotating counterclockwise in Neptune's southern hemisphere when Voyager flew by. By the time the Hubble Space Telescope looked at Neptune a few years later, that storm had vanished, replaced by new ones in different locations. The atmosphere that looks so peaceful from a distance is actually moving at supersonic speeds, with winds reaching 1,200 miles per hour, the fastest in the solar system. These winds might play a role in the distribution of diamonds throughout Neptune's atmosphere. As the diamonds form and begin to fall, they're not falling straight down. They're being carried by these incredible winds, swept sideways even as gravity pulls them deeper. A diamond that forms at one latitude might end up thousands of miles away by the time it reaches greater depths. It's a three-dimensional dance of pressure, temperature, chemistry, and fluid dynamics, all happening in slow motion by our standards, but creating a kind of planetary metabolism that's been running for billions of years. The colour of Neptune itself tells us something about its composition. That beautiful blue isn't from water, like Earth's blue, but from methane in the atmosphere absorbing red light and reflecting blue light back to space. It's the same methane that breaks down to form diamonds, the same simple molecule that we use for fuel here on Earth. In a sense, Neptune's colour is a visible sign of the chemistry that creates diamond rain. The blue planet rains diamonds because it is blue, and it is blue because it contains the ingredients for diamonds. As we contemplate this connection between colour and composition, between beauty and chemistry, we might wonder what other secrets are hidden in the colours of worlds. Every planet in our solar system has its own palette, its own chemical signature written in light. Mars is red from iron oxide. Jupiter is banded in browns and whites from different cloud compositions. Saturn is pale gold from ammonia haze. And Neptune is the deep blue of methane, the colour of diamond rain. The study of Neptune's diamond rain isn't just an exercise in exotic chemistry. It has implications for our understanding of planetary formation, for the evolution of solar systems, for the possibility of life elsewhere in the universe. If diamond rain is common on ice giant planets, and if ice giants are common in other solar systems, which they appear to be, then diamond rain might be happening on millions or billions of worlds throughout the galaxy. What seems impossibly exotic to us might be mundane on a cosmic scale. This realization brings us back to Earth with a new perspective. Our planet, with its liquid water rain, its oxygen atmosphere, its carbon-based life, might be the true exotic world in a universe full of diamond-raining ice giants. What we consider normal, the conditions we evolved in and depend on, might be the exception rather than the rule. Earth doesn't rain diamonds not because it's lacking something, but because it has something else, something perhaps even more remarkable, the conditions for life as we know it. The carbon that becomes diamonds on Neptune becomes something else entirely on Earth. Here, carbon forms the backbone of DNA, the structure of proteins, the energy currency of cells. It cycles through the atmosphere as carbon dioxide, through the oceans as carbonic acid and carbonates, through the rocks as limestone and coal and oil. It's the element of life, constantly transforming but never creating diamonds in our atmosphere because our atmosphere is too thin, too cool, too oxygen-rich for that particular transformation. But Earth does have diamonds. They form deep in our mantle, under conditions that are extreme by our surface standards, but mild compared to Neptune's atmosphere. These diamonds are then carried to the surface by volcanic eruptions, specifically by rare eruptions called kimberlites that originate deeper than normal volcanoes. The diamonds we mine and treasure are ancient, most of them over 1 billion years old, formed when Earth was young and then waiting in the darkness until geological chance brought them to where we could find them. The contrast is striking. On Earth, diamonds are rare accidents of geology, requiring special conditions and lucky circumstances to form, and then even luckier circumstances to reach the surface where we can find them. On Neptune, they're an inevitable consequence of atmospheric chemistry, forming continuously, falling constantly, abundant beyond measure but forever out of reach. It's as if the universe is playing a cosmic joke, making diamonds common where we can never go and rare where we live. Yet perhaps there's a deeper lesson in this contrast. The things we value, the things we consider precious, are precious precisely because of their context. A diamond on Neptune would be worthless in the economic sense because there are so many of them. But a diamond on Earth carries the weight of its journey, the billion-year story of its formation, the geological forces that brought it to the surface, the human effort to find and extract it. Value isn't intrinsic to the object. It emerges from the relationship between the object and its environment, between rarity and desire, between effort and reward. As we continue our journey through this cosmic mystery, let's pause for a moment to consider the scientists who figured this out. The idea that it might rain diamonds on Neptune didn't come from direct observation. No one has seen these diamonds. Instead, it came from careful reasoning, from understanding the physics of pressure and the chemistry of carbon, from laboratory experiments that replicated extreme conditions, from computer models that simulated atmospheric dynamics. It's a testament to human ingenuity that we can deduce the weather on a world we've barely visited, that we can understand processes happening under conditions we'll never experience. The first person to seriously propose diamond rain on ice giants was Marvin Ross, a physicist at Lawrence Livermore National Laboratory in 1981. He was studying the behavior of materials under extreme pressure, using shock waves to briefly create the kinds of conditions found in planetary interiors. When he calculated what would happen to methane under Neptune-like conditions, the math pointed to diamond formation. It was such an outlandish conclusion that it took years for the scientific community to fully accept it, but subsequent experiments and calculations have only strengthened the case. More recently, scientists have used some of the world's most powerful lasers to create these conditions in the laboratory. At the SLAC National Accelerator Laboratory, researchers used intense X-ray pulses to watch diamond formation happen in real time, compressing hydrocarbons to millions of atmospheres of pressure and watching as carbon atoms arrange themselves into diamond lattices. The process took nanoseconds in the lab, but the physics is the same as what happens over years in Neptune's atmosphere. It's like watching a billion-year process compressed into the blink of an eye. These experiments have revealed surprises. For instance, the diamonds that form under Neptune-like conditions might not be pure carbon. They might contain traces of hydrogen or other elements, creating unusual varieties of diamond that don't exist naturally on Earth. These alien diamonds might have different properties, different colours, different strengths than the diamonds we know. They might glow with their own light, or conduct electricity, or have other properties we haven't yet imagined. The process of diamond formation on Neptune might also create other, exotic materials. As the methane breaks down and the carbon forms diamonds, the leftover hydrogen doesn't just disappear. Under these extreme conditions, hydrogen itself becomes strange. It might form a metallic state, conducting electricity like a metal despite being the lightest element. This metallic hydrogen might surround the falling diamonds, creating a kind of sparkling soup of diamond and liquid metal, a mixture that exists nowhere on Earth and challenges our understanding of material science. Temperature plays a crucial role in this process. If it's too hot, diamonds won't form at all. The carbon will remain in other forms. If it's too cold, the chemical reactions slow down too much. Neptune's temperature profile, gradually increasing with depth, creates a specific zone where conditions are just right for diamond formation. It's like a cosmic Goldilocks zone, but instead of liquid water and life, it produces diamonds. Above this zone, it's too cold and the pressure is too low. Below this zone, it might be too hot, or the diamonds might transform into other forms of carbon we haven't discovered yet. The exact depth at which diamonds form on Neptune is still debated. Some models suggest it happens relatively high in the atmosphere, perhaps only a few thousand kilometers down. Others suggest it happens much deeper, closer to the planet's core. The truth might be that diamond formation happens across a broad range of depths, with different sizes and qualities of diamonds forming under different conditions. There might be a gentle snow of tiny diamonds in the upper regions, and a heavier rain of larger diamonds deeper down. Size is another mystery. How big do these diamonds get? On Earth, the largest diamonds are exceptional, formed under very specific conditions over very long times. But on Neptune, with constant formation and billions of years of accumulation, could there be diamonds the size of buildings? The size of mountains? We don't know. The dynamics of the atmosphere, the winds and convection currents, might break up large diamonds before they can grow too big. Or perhaps in the calmer depths, away from the supersonic winds, diamonds can grow to enormous sizes, floating in the metallic hydrogen like icebergs in an alien sea. The rate of diamond formation is equally uncertain. How many tons of diamond form each day on Neptune? Each year? Over the life of the planet? Conservative estimates suggest that the total mass of diamond on Neptune could be millions of times greater than all the carbon on Earth. But these are just estimates, based on models that might be missing important factors. The true amount could be much more or much less. It's humbling to realize that one of the basic facts about our solar system, how much diamond exists on Neptune, is unknown and might remain unknown for generations. This uncertainty extends to the ultimate fate of these diamonds. Do they accumulate in a layer? Do they eventually dissolve back into the fluid interior? Do they sink all the way to Neptune's core? Each possibility has different implications for the planet's structure and evolution. If diamonds accumulate in a layer, they might affect how heat flows through the planet. If they dissolve, they might create convection currents that power Neptune's magnetic field. If they reach the core, they might form a diamond shell around whatever lies at Neptune's center. Neptune's magnetic field is another puzzle that might be related to diamond rain. Unlike Earth's magnetic field, which is roughly aligned with our rotation axis, Neptune's magnetic field is tilted at a sharp angle and offset from the planet's center. This unusual configuration might be related to the complex circulation patterns in Neptune's interior, patterns that could be influenced by falling diamonds. The diamonds, being denser than the surrounding fluid, might create currents as they fall, and these currents might generate or modify the magnetic field. The interaction between diamonds and Neptune's magnetic field could create other phenomena we haven't imagined. Moving diamonds in a magnetic field could generate electric currents. These currents could heat the surrounding fluid, create electromagnetic radiation, or produce other effects. Neptune's interior might be alive with electrical activity, a natural dynamo powered by diamond rain. It's a possibility that sounds like science fiction but follows from the basic physics of moving charged or conductive particles in magnetic fields. As we delve deeper into this mystery, we find connections to other mysteries. For instance, Neptune radiates about 2.6 times more energy than it receives from the Sun. Where does this extra energy come from? Part of it is probably leftover heat from the planet's formation, still slowly leaking out after billions of years. But part of it might come from the gravitational energy released by falling diamonds, or from chemical energy released by the breakdown of methane, or from other processes we haven't yet understood. The diamond rain might be just one part of a complex energy budget that keeps Neptune warm in the cold outer solar system. The seasonal cycles on Neptune, if we can call them that, are unlike anything on Earth. Neptune's year is 165 Earth years long. A season on Neptune lasts over 40 years. Imagine winter lasting from your birth until middle age, then spring arriving as you approach retirement. These long seasons might affect the diamond rain. Perhaps during Neptune's summer, the upper atmosphere warms slightly, changing the depth at which diamonds form. Perhaps the rate of diamond formation varies over Neptune's long year, creating epochs of heavy diamond rain alternating with periods of lighter precipitation. But even the concept of seasons on Neptune is strange. The planet is so far from the Sun that sunlight is 900 times weaker than on Earth. The Sun from Neptune would look like a very bright star, not the warming disk we know. Most of Neptune's weather is driven not by solar heating but by internal heat, by the energy flowing up from its deep interior. The diamond rain might be more important for Neptune's weather than the distant Sun. This brings us to a profound realization. Neptune's diamond rain is a closed system, independent of the Sun, running on the planet's internal energy. It's a process that could continue even if the Sun went out, as long as Neptune retained its internal heat and its reservoir of methane. In a sense, the diamond rain is more fundamental to Neptune than its orbit around the Sun. It's a process that defines the planet at a deep level, shaping its structure, its evolution, its very nature. As we contemplate these vast scales of time and space, these extreme conditions and exotic processes, it's natural to wonder, could we ever harvest these diamonds? Could future humans travel to Neptune and collect the diamonds raining through its atmosphere? The practical answer is almost certainly no. The conditions that create the diamonds would destroy any spacecraft we could build. The pressures would crush any material we know. The temperatures would vaporize any probe long before it reached the diamond-forming depths. And even if we could somehow collect diamonds from Neptune, the energy required to travel there and back would far exceed any value the diamonds could have. But perhaps that's not the right question. Perhaps the value of Neptune's diamonds isn't economic, but philosophical. They remind us that the universe is far stranger and more wonderful than our everyday experience suggests. They show us that processes we consider impossible are happening right now, have been happening for billions of years, in our own cosmic backyard. They teach us humility about what we think we know and inspire us to keep exploring, keep questioning, keep wondering. The diamond rain on Neptune also connects to broader questions about planetary formation and evolution throughout the universe. We've discovered thousands of planets orbiting other stars, and many of them are similar in size and mass to Neptune. If our understanding is correct, many of these worlds might also have diamond rain. There might be millions or billions of planets in our galaxy where diamonds fall like rain through crushing darkness. Each of these worlds would be slightly different, with its own chemistry, its own temperature profile, its own unique form of diamond precipitation. Some of these worlds might be even more extreme than Neptune. We've discovered exoplanets that orbit much closer to their stars, hot Neptunes, with temperatures that would vaporize any diamond. We've found planets much more massive than Neptune, super Neptunes, where the pressures might create forms of carbon we haven't even theorized yet. Each of these worlds expands our understanding of what's possible, of the range, of conditions and processes that can exist in the universe. The study of exoplanets has revealed that our solar system, which once seemed like the template for all planetary systems, might actually be unusual. Many other systems have giant planets close to their stars, or planets in highly elliptical orbits, or arrangements that seem unstable by our standards. In this context, Neptune's diamond rain might be just one example of the exotic processes happening throughout the cosmos, processes that challenge our Earth-centered assumptions about how planets work. This cosmic perspective brings us back to Earth with fresh eyes. Our planet's carbon cycle, the way carbon moves through atmosphere, oceans, rocks, and life, is just one possible carbon cycle among many. On Neptune, carbon follows a different path, from methane to diamond, falling through layers of increasing pressure and temperature. On Venus, carbon is locked in a dense carbon dioxide atmosphere that creates a runaway greenhouse effect. On Mars, carbon is frozen in polar caps and absorbed in rocks. Each planet has found its own solution to the question of what to do with carbon. Life on Earth has evolved to use carbon as its fundamental building block, creating millions of different carbon-based molecules that form the basis of biology. But if life exists elsewhere, on worlds with different chemistries and conditions, it might use carbon very differently, or might not use carbon at all. The diamond rain on Neptune reminds us that carbon can do things we never imagined, can exist in states we never encountered, can follow paths we never considered. If carbon can become diamond rain, what else might be possible? As we near the end of this first part of our journey, let's return to that image of diamonds falling through Neptune's atmosphere. Picture them in your mind, crystals of pure carbon formed under impossible pressures, falling through eternal darkness, carried by supersonic winds, descending through layers of exotic chemistry toward an unknown fate. They've been falling since before Earth had life. They'll continue falling long after our sun has died. They're falling right now as you listen to these words, as you breathe, as your heart beats. There's something deeply peaceful about this image, isn't there? The diamonds don't fall with urgency or violence. They fall with the same patient grace that governs all the great processes of the universe. They're in no hurry. They have nowhere specific to go. They simply fall, obeying the laws of physics, following their nature, participating in the slow metabolism of a planet we've barely glimpsed. And in their falling, they tell us something important about the universe and our place in it. They remind us that we live in a cosmos where the impossible happens regularly, where beauty emerges from extreme conditions, where even the most common elements can surprise us. They show us that our earthly perspective, precious as it is just one viewpoint among countless others. They invite us to expand our imagination, to consider possibilities we haven't dreamed of, to remain humble before the vastness and strangeness of existence. The diamonds of Neptune will never adorn anyone's finger, never sparkle in anyone's crown, never symbolize anyone's love. But perhaps that makes them more precious, not less. They exist for their own sake, following their own nature, independent of human desire or valuation. They're pure in a way that earthly diamonds can never be, untouched by human hands, unshaped by human tools, participating in a process that predates us and will outlast us. As you drift towards sleep tonight, perhaps you'll dream of Neptune's diamonds. Perhaps you'll imagine yourself floating in that blue atmosphere, watching crystals form from methane and pressure, watching them begin their long fall toward the planet's heart. Perhaps you'll feel the peace of that eternal rain, the patience of geological time, the beauty of processes that need no witness to be complete. But before we continue deeper into this mystery, let's pause here. At the threshold between the known and the unknown, between the world we inhabit and the worlds we can only imagine. We've established the basic facts. Neptune exists. It contains methane. The conditions in its atmosphere can transform methane into diamond, and those diamonds must fall deeper into the planet. But so many questions remain. How did scientists figure this out? What exactly happens in those laboratories that recreate Neptune's conditions? What other secrets might be hidden in the deep atmospheres of giant planets? These questions lead us deeper into one of the most remarkable detective stories in planetary science. The journey to understanding diamond rain on Neptune didn't begin with Neptune at all. It began here on Earth, in laboratories where scientists were trying to understand what happens to materials under extreme pressure. They weren't looking for diamonds in the sky. They were trying to understand the fundamental behavior of matter when it's squeezed beyond all normal experience. But as often happens in science, the search for one answer revealed something far more extraordinary. Picture a laboratory in the early 1980s. Marvin Ross, a physicist at Lawrence Livermore National Laboratory in California, is working with shockwave experiments. These experiments involve firing projectiles at incredible speeds into samples of material, creating pressures that exist for only microseconds but replicate conditions found deep inside planets. Ross isn't thinking about Neptune specifically. He's thinking about methane, one of the simplest organic molecules, and what happens to it under pressure. The calculations are complex, involving quantum mechanics and thermodynamics, but the conclusion is startling. At pressures above a certain threshold, methane should decompose, and the carbon should crystallize into diamond. At first, this seemed like just an interesting theoretical result, but then Ross made the connection. These pressures, millions of times atmospheric pressure, don't exist naturally on Earth, except perhaps for brief moments during meteor impacts. But they do exist inside giant planets. Jupiter, Saturn, Uranus and Neptune all have the mass to create such pressures in their interiors, and Uranus and Neptune, the ice giants, have significant amounts of methane in their atmospheres. The pieces of the puzzle suddenly fit together. If the physics was right, if the calculations were correct, then it should be raining diamonds inside these distant worlds. The scientific community was skeptical, as it should be when faced with such an extraordinary claim. Diamonds falling like rain through alien atmospheres. It sounded more like science fiction than science fact. But Ross had done his homework. The physics was solid. The chemistry made sense. The conditions existed. Still, theoretical predictions are one thing. Experimental confirmation is another. The challenge was how to test this hypothesis when the nearest ice giant is over 1 billion miles away, and the conditions needed to form diamonds from methane are so extreme that they seemed impossible to recreate on Earth. This is where the story becomes a testament to human ingenuity and technological advancement. Scientists couldn't go to Neptune, so they had to bring Neptune's conditions to Earth. They needed to create pressures of millions of atmospheres and temperatures of thousands of degrees, maintain those conditions long enough to observe what happens, and do it all in a controlled, measurable way. It seemed impossible, but over the decades following Ross's prediction, that's exactly what scientists learned to do. The first tool in this quest was the diamond anvil cell, a device that seems almost poetically appropriate for studying diamond formation. The principle is simple. Take 2 diamonds, the hardest natural material we know, shape them into anvils with tiny flat surfaces, and squeeze a sample between them. Because the surfaces are so small, even a moderate force creates enormous pressure. The diamonds are transparent so scientists can shine light through them to observe what happens to the sample. With laser heating, they can also create high temperatures. is like having a window into the deep interior of a planet, albeit a very tiny window. Using diamond anvil cells, scientists in the 1990s and 2000s began to map out the behavior of hydrocarbons under extreme conditions. They discovered that methane does indeed break down under pressure, just as Ross had predicted. They watched as carbon atoms freed from their hydrogen bonds began to cluster together. But seeing actual diamond formation was challenging. The samples were microscopic, the conditions were difficult to maintain, and the transformation from methane to diamond happened at conditions right at the edge of what the equipment could achieve. The breakthrough came with the development of even more powerful experimental techniques. At facilities like the SLAC National Accelerator Laboratory at Stanford, scientists could use the world's most powerful X-ray lasers to create and probe extreme conditions. These experiments were like lightning strikes in reverse, focusing enormous energy into tiny spaces for incredibly brief moments. In 2017, a team led by Dominic Krauss finally achieved what many had thought impossible. They watched in real time as hydrocarbons transformed into diamonds under Neptune-like conditions. The experiment was elegant in its conception. The team used polystyrene, a plastic made of carbon and hydrogen, as a stand-in for methane. They hit the plastic with powerful laser pulses, creating shock waves that generated pressures of up to 150 gigapascals, about 1.5 million times atmospheric pressure, and temperatures of about 5,000 Kelvin. Using ultra-fast X-ray diffraction, they could see the atomic structure of the material as it transformed, and transform it did. Within nanoseconds, they observed carbon atoms arranging themselves into the characteristic lattice structure of diamond. But this wasn't just any diamond formation. The conditions were so extreme that the diamonds formed through a process unlike anything that happens naturally on Earth. On our planet, diamonds form slowly over millions of years as carbon-bearing minerals are subjected to steady pressure and temperature. In the laser experiments, and presumably on Neptune, diamonds form almost instantaneously as methane molecules are ripped apart by pressure and the freed carbon atoms immediately crystallize. It's diamond formation in fast-forward, a billion-year process compressed into billionths of a second. The experiments revealed other surprises too. The diamonds that formed weren't pure carbon. They contained traces of hydrogen, creating what scientists call hydrogenated diamonds. These aren't like any diamonds found on Earth. The hydrogen atoms trapped in the diamond lattice might give these Neptune diamonds different properties, different colors, different electrical conductivity, perhaps even different mechanical properties. They're alien diamonds in the truest sense, materials that exist nowhere in our earthly experience. As experimental techniques improved, scientists could explore a wider range of conditions. They discovered that diamond formation from hydrocarbons isn't a simple on-off process. There's a complex phase diagram, a map of different states of carbon at different pressures and temperatures. At some conditions, carbon forms graphite. At others, it forms diamond. At still others, it might form exotic phases with names like BC8 or simple cubic carbon, structures that are theoretically possible but have never been found in nature on Earth. Neptune's interior might contain all of these phases, layers of different carbon structures depending on the local conditions. The size of diamonds that form under these conditions was another revelation. In the laboratory experiments, the diamonds were tiny, nanometers across, visible only through X-ray diffraction. But the experiments lasted only nanoseconds. On Neptune, the process has been running for billions of years. Given time, these nanodiamonds could grow. They could merge together, forming larger crystals. They could accumulate into layers. The patient accretion of crystal upon crystal over geological time could create diamonds of extraordinary size. Computer simulations have become another crucial tool in understanding Neptune's diamond rain. Modern supercomputers can model the behavior of millions of atoms under extreme conditions, tracking how they move, how they bond, how they transform. These simulations have revealed the detailed mechanics of diamond formation, how methane molecules vibrate faster and faster as pressure increases, how the carbon-hydrogen bonds stretch and finally snap, how the freed carbon atoms find each other in the chaos and lock into crystalline perfection. The simulations also show something beautiful. The formation of diamond from methane under pressure is almost inevitable. It's not a rare accident or a delicate balance. Once the conditions are right, the transformation happens spontaneously, driven by thermodynamics. Diamond is simply the most stable form of carbon at those pressures and temperatures. The universe, in its fundamental laws, demands that carbon become diamond under Neptune's conditions. It's as natural and inevitable as water freezing into ice or iron rusting in oxygen. But the laboratory experiments and computer simulations, impressive as they are, still leave us far from truly understanding what happens on Neptune. The experiments last nanoseconds or at most microseconds. Neptune's diamond rain has been falling for billions of years. The experiments use microscopic samples. Neptune's atmosphere contains more methane than exists on Earth. The experiments happen in isolated chambers. Neptune's diamond rain occurs in a dynamic, convecting, rotating atmosphere with complex chemistry and powerful magnetic fields. Scaling up from the laboratory to the planet requires imagination, mathematical modelling, and a healthy appreciation for uncertainty. This is where planetary scientists become detectives, piecing together clues from multiple sources to build a picture of something they can't directly observe. They take the laboratory results that show diamonds can form from methane under pressure. They combine this with spectroscopic observations of Neptune that reveal methane in its atmosphere. They add models of Neptune's interior structure based on its mass, radius, and gravitational field. They factor in the heat flow measurements that show Neptune radiating more energy than it receives. Each piece of evidence constrains the possibilities, narrowing down the range of what might be happening inside the planet. The models that emerge from this synthesis are remarkable in their detail, even as they acknowledge vast uncertainties. They suggest that Neptune's interior can be divided into several layers. The outermost layer is the visible atmosphere, mostly hydrogen and helium with traces of methane that give the planet its blue color. Below this is a region where pressure and temperature increase rapidly with depth. Somewhere in this region, perhaps a few thousand kilometers down, conditions become right for diamond formation. The model suggests this diamond-forming region might be thousands of kilometers thick, a vast zone where methane continuously breaks down and carbon crystallizes. Below the diamond-forming region, the models become more uncertain. Perhaps there's a layer where diamonds accumulate, unable to sink further because of increasing density or changing composition. Perhaps the diamonds continue falling until they reach a core of rock and ice, where they might form a layer of diamond around the core, or perhaps they dissolve back into the metallic hydrogen that might exist at the greatest depths, their carbon atoms beginning a new journey that might eventually take them back up to where they can form diamonds again. The circulation patterns in Neptune's interior add another layer of complexity. The planet rotates once every 16 hours, and this rotation, combined with convection driven by internal heat, creates complex flow patterns. The falling diamonds don't just drop straight down, they're carried by these currents, swept sideways, perhaps cycled up and down in giant convection cells. It's a three-dimensional dance of fluid dynamics, chemistry, and crystallization, all happening in slow motion by our standards, but shaping the planet over cosmic time. The magnetic field measurements from Voyager 2 provide another piece of the puzzle. Neptune's magnetic field is tilted and offset, suggesting that it's generated not in the core, as Earth's is, but in the mantle, perhaps in the very region where diamonds are forming and falling. The movement of electrically conductive material, possibly metallic hydrogen mixed with falling diamonds, could generate this field. The diamonds themselves might play a role, their movement through the magnetic field inducing currents that strengthen or modify the field. It's a complex feedback system where chemistry, physics, and planetary dynamics all interact. Temperature is a critical factor that we're still trying to understand. The temperature profile of Neptune's interior, how temperature changes with depth, determines where diamonds can form and how long they survive. If it gets too hot too quickly with depth, diamonds might form only in a narrow zone. If the temperature increases more gradually, the diamond-forming region could be very thick. The temperature also affects the size of diamonds that can form, the rate at which they grow, and whether they eventually transform into other forms of carbon. Recent observations from ground-based telescopes and the Hubble Space Telescope have added new constraints to our models. By carefully measuring Neptune's infrared emission, scientists can estimate how much heat is flowing out of the planet. By tracking the movement of clouds and storms, they can infer wind patterns and atmospheric dynamics. By analysing the spectrum of light reflected from Neptune, they can measure the abundance of different molecules in the visible atmosphere. Each observation adds a piece to the puzzle, helping to refine our understanding of what's happening inside the planet. One of the most intriguing recent discoveries is that Neptune's atmosphere seems to be changing over time. Long-term observations show variations in cloud patterns, storm activity, and even the planet's overall brightness. These changes might be seasonal, related to Neptune's 165-year orbit around the Sun, or they might be driven by longer-term cycles we don't yet understand. Could the rate of diamond formation vary with these cycles? Could changes in the upper atmosphere affect conditions in the diamond-forming region below? These are questions we're only beginning to explore. The interaction between diamond rain and Neptune's heat budget is particularly fascinating. Every diamond that falls releases gravitational potential energy, which becomes heat. This heat then drives convection, which brings more methane into the diamond-forming region. It's a self-sustaining process, a heat engine powered by crystallization. But how efficient is this engine? How much of Neptune's internal heat comes from diamond rain versus other sources like radioactive decay or leftover heat from formation? Models suggest diamond rain could be a significant contributor, but the exact amount remains uncertain. The chemistry of Neptune's interior is far more complex than just methane breaking down into diamond and hydrogen. The atmosphere contains other molecules too: ammonia, water, hydrogen sulfide, and various hydrocarbons. These might interact with the diamond formation process in complex ways. Water, for example, might react with methane under pressure to form carbon monoxide or carbon dioxide instead of diamond. Ammonia might form compounds with carbon that affect crystallization. The real chemistry of Neptune's interior is probably a rich soup of reactions we're only beginning to understand. Laboratory experiments are now exploring these more complex chemistries. Instead of pure methane or simple hydrocarbons, scientists are experimenting with mixtures that more closely match Neptune's composition. They're discovering that the presence of other molecules can either enhance or inhibit diamond formation, depending on the conditions. Some additives might act as catalysts, speeding up diamond formation. Others might poison the process, preventing crystals from growing. The real Neptune is undoubtedly more complex than our simplified models suggest. The question of diamond size remains one of the most tantalizing unknowns. In the laboratory, we can only create nanodiamonds in the brief moments of our experiments. But on Neptune, diamonds have had billions of years to grow. Could individual diamonds grow to enormous sizes, like the giant crystals found in some caves on Earth? Or do the dynamics of Neptune's interior prevent large diamonds from forming, constantly breaking them up or limiting their growth? The answer might depend on the specific conditions at different depths, with different zones producing different sizes of diamonds. There's also the question of diamond quality. On Earth, we classify diamonds by their clarity, colour, and other properties. Neptune's diamonds, formed under such extreme conditions and potentially containing impurities like hydrogen, might have properties we've never seen. They might be coloured by trace elements or structural defects. They might be electrically conductive or have unusual optical properties. They might be stronger or weaker than Earth diamonds depending on their structure and composition. Each diamond falling through Neptune's atmosphere is potentially unique, shaped by the specific conditions of its formation. The rate of diamond formation is another major uncertainty. How much diamond forms each year on Neptune? The answer depends on many factors: the amount of methane in the atmosphere, the size of the diamond-forming region, the efficiency of the conversion process, and the rate at which methane is transported into the diamond-forming zone. Estimates range from thousands to millions of tons per year, but these are really just educated guesses based on our incomplete understanding of Neptune's interior. If we could somehow observe Neptune's interior directly, what would we see? Perhaps we would see a continuous gentle snow of tiny diamonds, sparkling as they fall through the dense atmosphere. Or perhaps we would see occasional larger crystals tumbling slowly through the murk. The diamonds might be concentrated in certain regions, following convection patterns or accumulating in layers. Or they might be distributed throughout a vast region, a three-dimensional blizzard in slow motion. The reality is probably more complex and beautiful than anything we've imagined. The implications of diamond rain extend beyond Neptune itself. If our understanding is correct, then similar processes should be happening on Uranus, Neptune's twin ice giant. Uranus is slightly smaller and cooler than Neptune, which might mean diamonds form at different depths or at different rates. But the basic process should be the same. This means our solar system has not one but two planets, where it's raining diamonds right now. And if ice giants in other solar systems are similar, There could be millions or billions of planets throughout the galaxy, where diamonds fall like rain. This universality of diamond rain speaks to something profound about the nature of matter and the cosmos. The same carbon atoms that form proteins in our bodies, that make up the graphite in pencils, that become coal and oil in Earth's crust, these same atoms become diamonds when subjected to the conditions inside ice giants. The universe has many ways of arranging carbon atoms, and each arrangement tells us something about the conditions that created it. Diamond rain is just one particularly spectacular example of this cosmic chemistry. As we delve deeper into the mechanisms of diamond formation on Neptune, we find connections to fundamental questions in physics and chemistry. The behavior of matter under extreme pressure touches on quantum mechanics, as electrons are forced into new configurations. The transformation from methane to diamond involves breaking and forming chemical bonds in ways that test our understanding of chemistry. The dynamics of falling diamonds in a convecting atmosphere involves fluid dynamics, at scales and conditions we can barely imagine. Every aspect of diamond rain pushes the boundaries of our scientific understanding. The role of time in this process cannot be overstated. On Earth, we're used to weather that changes by the hour, storms that last days, seasons that cycle annually. But Neptune's diamond rain operates on geological timescales. A single diamond might take thousands of years to fall from its point of formation to wherever it finally comes to rest. The convection cycles that bring methane into the diamond-forming region might take millions of years to complete. The accumulation of diamonds in layers, if it occurs, has been happening for billions of years. This is weather in slow motion, meteorology on a planetary timescale. The energy involved in Neptune's diamond rain is staggering when considered in aggregate. Each falling diamond releases a tiny amount of gravitational potential energy. But multiply that by the countless diamonds falling at any given moment, and then by the billions of years this process has been running, and the total energy becomes enormous. This energy doesn't disappear. It becomes heat, driving convection, powering weather, possibly contributing to Neptune's magnetic field. The diamond rain is part of Neptune's energy economy, a way the planet converts gravitational potential energy into other forms. Understanding this energy flow has implications for planetary evolution. How has Neptune changed over its lifetime as diamonds accumulated in its interior? Has the rate of diamond formation changed as the planet cooled? Will it continue raining diamonds for billions more years, or will the process eventually slow and stop as the planet runs out of methane or cools below the threshold for diamond formation? These questions connect to broader issues of planetary life cycles and the long-term evolution of solar systems. The technology we've developed to study diamond rain has applications beyond planetary science. The same techniques used to create extreme pressures and temperatures in the laboratory are used to study materials for technology, to understand the Earth's deep interior, to explore new states of matter. The computational methods developed to model Neptune's interior are applied to everything from climate modeling to drug design. The quest to understand diamond rain on a distant planet has led to advances that benefit many fields of science and technology. There's something profound about the fact that we can understand, even partially, a process happening billions of miles away under conditions we'll never directly experience. It speaks to the power of scientific reasoning, the universality of physical laws, and the human capacity for imagination and deduction. We've taken observations from a brief spacecraft flyby, experiments in Earth laboratories, and theoretical calculations, and from these fragments, we've pieced together a picture of one of the most exotic weather systems in our solar system. Yet for all our understanding, diamond rain on Neptune remains fundamentally alien to human experience. We can calculate it, model it, even recreate it in miniature, but we can't truly comprehend what it would be like to witness diamonds falling through an atmosphere denser than water, in darkness, absolute, under pressures that would crush any material we could build, at temperatures that would vaporize any probe we could send. The diamond rain exists in a realm beyond direct human experience, accessible only through the tools and imagination of science. This brings us to a philosophical question. What does it mean to understand something we can never experience? Our knowledge of Neptune's diamond rain is entirely mediated through instruments, calculations, and models. We've never seen these diamonds, never touched them, never watched them fall. Our understanding is abstract, mathematical, removed from sensory experience. And yet, the physics tells us the diamonds are real as the diamonds in Earth's crust, falling through Neptune's atmosphere at this very moment whether we observe them or not. The search for understanding Neptune's diamond rain has also revealed how much we don't know. Every answer raises new questions. If diamonds form from methane, what happens to the hydrogen? How does it interact with the falling diamonds? Does it form its own exotic structures under pressure? If diamonds accumulate in layers, how thick are these layers? Do they affect Neptune's seismic properties? Could we detect them with the right instruments? The more we learn, the more we realize the complexity of what's happening inside Neptune. One of the most intriguing unknowns is whether the diamond rain creates any observable signatures that we could detect from Earth or from future space missions. Do the falling diamonds create acoustic waves, pressure waves that propagate through Neptune's interior? Do they affect the planet's gravitational field in measurable ways? Do they create electromagnetic signatures as they interact with Neptune's magnetic field? These are the kinds of questions that might guide future observations and missions to the outer solar system. The possibility of future missions to Neptune adds excitement to this field of study. While no missions are currently approved, scientists have proposed various concepts for Neptune orbiters and atmospheric probes. These missions could carry instruments specifically designed to study the diamond rain, spectrometers to measure atmospheric composition at different depths, seismometers to detect the acoustic signatures of falling diamonds, magnetometers to map the magnetic field in detail. Such missions are technically challenging and would take decades to plan, build, and fly, but they could revolutionize our understanding of ice giants and their exotic weather. In the meantime, advances in Earth-based observations continue to refine our picture of Neptune. New telescopes with adaptive optics can see details on Neptune that were invisible just a few years ago. The James Webb Space Telescope is providing unprecedented infrared observations of Neptune's atmosphere. Future telescopes, both on the ground and in space, will push these observations even further. Each improvement in our observational capabilities adds new constraints to our models of what's happening inside the planet. The study of exoplanets, planets orbiting other stars, provides another avenue for understanding diamond rain. Many of the exoplanets we've discovered are similar in size and mass to Neptune, suggesting they might be ice giants with similar compositions and conditions. By studying the statistics of these planets, their frequencies, sizes, and orbits, we can better understand how common ice giants are and, by extension, how common diamond rain might be in the universe. Some of these exoplanets orbit much closer to their stars, creating hot Neptunes, where the chemistry might be different but equally exotic. The diversity of exoplanets suggests that diamond rain might take many forms on different worlds. On a planet more massive than Neptune, the pressures would be even higher, possibly creating forms of carbon we haven't yet imagined. On a planet with different chemistry, other elements might form their own kinds of exotic precipitation. Silicon might form crystals of quartz or other minerals. Sulfur might form its own exotic compounds. Each planet might have its own unique form of deep atmosphere precipitation, its own version of Neptune's diamond rain. This cosmic perspective reminds us that our solar system, familiar as it seems, is just one example of planetary systems and perhaps not even a typical one. The processes we're discovering on Neptune might be common throughout the universe, or they might be relatively rare. We don't yet know. But the fact that we can even ask these questions, that we can study the weather on a planet billions of miles away, and speculate about weather on planets orbiting other stars, is a testament to human curiosity and ingenuity. As we continue to study Neptune's diamond rain, we're also developing new ways of thinking about planetary interiors. The traditional view of planets as having distinct layers like an onion is giving way to a more dynamic picture of convecting, reacting, transforming materials. The interior of Neptune isn't static, it's a slowly churning engine of chemistry and physics, with diamond rain as one of its most spectacular products. This dynamic view applies to other planets too, including Earth, where we're discovering that the deep interior is far more active and complex than previously thought. The connection between Neptune's diamond rain and Earth's geology is more than just analogical. Both involve carbon under pressure, though at very different scales. Both involve the transformation of one form of carbon into another. Both are driven by the fundamental thermodynamics of stability under different conditions. Studying Neptune's diamonds helps us understand Earth's diamonds, and vice versa. It's a reminder that the same physical laws govern processes across the universe, from the formation of diamonds in Earth's mantle to their formation in Neptune's atmosphere. The timescales involved in Neptune's diamond rain challenge our perception of change and permanence. We think of diamonds as eternal, unchanging, the hardest natural material. But on Neptune, diamonds are constantly forming and potentially dissolving or transforming. They're part of a cycle, a process, not permanent fixtures. This challenges our assumptions about materials and their properties. Even diamond, that symbol of permanence, is temporary on cosmic timescales, subject to the patient forces of pressure, temperature, and time. The aesthetic dimension of diamond rain shouldn't be overlooked either. There's a beauty to the idea of diamonds falling through an alien atmosphere, a poetry to carbon crystallizing in the darkness. Science often reveals beauty in unexpected places, and the interior of Neptune, hostile and alien as it is, has its own strange magnificence. The diamonds themselves, could we see them, might be beautiful beyond imagination, shaped by forces and conditions that create forms impossible on Earth. As we prepare to explore the third aspect of our cosmic mystery, the comparison between Neptune and Earth, and what it tells us about planetary diversity, let's pause to appreciate how far we've come in understanding this phenomenon. From theoretical prediction to laboratory confirmation to detailed modelling, the story of discovering diamond rain on Neptune showcases science at its best: curious, rigorous, creative, and always reaching for deeper understanding. The diamonds falling through Neptune's atmosphere are more than just exotic precipitation. They're a window into the fundamental workings of planets, the behaviour of matter under extreme conditions, and the wonderful strangeness of our universe. The comparison between Earth and Neptune reveals something profound about the nature of planets and the conditions that shape them. Earth, our familiar blue marble, seems to have everything Neptune has in terms of basic ingredients. We have carbon in abundance, cycling through our atmosphere as carbon dioxide, buried in our rocks as carbonates, flowing through life as organic molecules. We have pressure too, increasing steadily as you descend through our planet's interior. We have heat, radiating up from our core, driving plate tectonics and volcanism. Yet despite having all these ingredients, Earth doesn't rain diamonds. The reason why tells us something fundamental about what makes each world unique. Earth's relationship with carbon is intimate and complex, but it follows very different pathways than on Neptune. Here, carbon is the element of life, the backbone of proteins and DNA, the foundation of every cell in every organism that has ever lived. Our carbon doesn't get compressed into diamonds in the atmosphere because our atmosphere is far too thin, a mere whisper compared to Neptune's crushing depths. At sea level, we experience 1 atmosphere of pressure. At the bottom of the deepest ocean trench, it's about 1,000 atmospheres. But to form diamonds from methane, you need millions of atmospheres, pressures that simply don't exist in Earth's fluid envelopes. But Earth does have diamonds, and their story is perhaps even more remarkable than Neptune's diamond rain, though it unfolds in a completely different theatre. Deep in Earth's mantle, typically at depths greater than 150 kilometres, conditions do become extreme enough for diamond formation, but the process is nothing like the rapid crystallization happening on Neptune. Earth's diamonds form over billions of years, carbon atoms slowly, patiently arranging themselves into crystalline perfection as they're subjected to the steady pressure and heat of the deep Earth. The carbon that becomes diamond on Earth has a different source too. Some of it is primordial, carbon that was part of Earth when it formed 4.5 billion years ago. Some of it is recycled from the surface, carried down by subducting oceanic plates that drag carbon-bearing sediments and rocks into the mantle. This carbon might have once been part of ancient life, shells and bones and plant matter compressed into limestone, then carried into the depths where pressure and heat transform it into something entirely different. In a sense, some of Earth's diamonds are made from ancient life, a transformation as profound as anything happening on Neptune. The journey of Earth's diamonds to the surface is equally remarkable. They don't fall like rain, they rocket upward in violent volcanic eruptions called kimberlites. These eruptions originate deeper than normal volcanoes, perhaps 200 kilometers or more below the surface. They rise with incredible speed, perhaps travelling from mantle to surface in a matter of hours or days, carrying diamonds and other deep minerals with them. If the ascent was slower, the diamonds would transform back into graphite as pressure decreased. It's only the speed of the eruption that preserves them in their diamond form, freezing them in a state that's actually unstable at Earth's surface. Think about that for a moment. The diamonds in jewellery stores, the diamonds in engagement rings, they're not actually stable at the conditions where we live. Given enough time, they should all turn back into graphite. The reason they don't is kinetic, not thermodynamic. The transformation is so slow at surface temperatures that diamonds persist for billions of years. They're metastable, caught in a form that shouldn't exist here but does because the universe hasn't had time to correct the situation. We wear diamonds that are, in a cosmic sense, mistakes that haven't been fixed yet. This contrast with Neptune's diamonds couldn't be more stark. Neptune's diamonds are forming right now, continuously, inevitably, as a natural consequence of the planet's conditions. Earth's diamonds formed long ago, preserved by geological accident, brought to the surface by rare volcanic events. Neptune's diamonds are abundant beyond measure. Earth's diamonds are genuinely rare, requiring a chain of unlikely circumstances to form and survive. Neptune's diamonds fall down. Earth's diamonds shoot up. The same element, the same crystal structure, but manifested through completely different planetary processes. The difference in how Earth and Neptune handle carbon extends beyond just diamond formation. Earth's carbon cycle is dominated by life and water. Carbon dioxide dissolves in our oceans, forming carbonic acid. Marine organisms use dissolved carbon to build shells and skeletons of calcium carbonate. When these organisms die, their remains sink to the ocean floor, eventually forming limestone and other carbonate rocks. Plate tectonics then recycles some of this carbon, releasing it through volcanoes back into the atmosphere. It's a complex dance involving biology, chemistry and geology, unique to a planet with liquid water and life. Neptune has no such cycle. Its carbon is locked in methane and other hydrocarbons, transformed by pressure into diamond, possibly accumulating in layers we can only imagine. There's no biology to complicate things, no liquid water to dissolve gases, no plate tectonics to recycle materials. The chemistry is simpler in some ways, but leads to more exotic outcomes. Where Earth creates limestone and coal, Neptune creates diamonds. Where Earth cycles carbon through living things, Neptune crystallizes it in the darkness. The temperature profiles of the two planets tell another part of the story. Earth's interior is hot, heated by radioactive decay and residual heat from formation, but the temperature increases gradually with depth, and there are no sharp transitions that would create distinct chemical zones. Neptune's interior, by contrast, has extreme temperature gradients, regions where conditions change rapidly with depth, creating distinct zones where different chemistry dominates. The diamond-forming region on Neptune exists because of a specific combination of temperature and pressure that occurs at a particular depth. Earth has no equivalent zone. Water plays a crucial role in why Earth doesn't rain diamonds. Our planet is, famously, the water world, with oceans covering 70% of the surface and water cycling through the atmosphere, crust, and mantle. Water affects carbon chemistry profoundly. It dissolves carbon dioxide, reacts with minerals, enables life. In Earth's mantle, even small amounts of water change how rocks melt, how minerals form, how carbon behaves. Water and carbon together create carbonates, not diamonds, under most conditions on Earth. Neptune has water too, but it's locked in ice or mixed with ammonia and methane in ways that create very different chemistry. The presence of free oxygen in Earth's atmosphere is another crucial difference. Our oxygen, produced by photosynthesis and maintained by life, creates an oxidizing environment where carbon tends to form carbon dioxide rather than diamonds. Methane is unstable in our oxygen-rich atmosphere. It quickly oxidizes to carbon dioxide and water. This is why natural gas leaks are temporary, and why methane from swamps and marshes doesn't accumulate to high concentrations. Neptune has no free oxygen, allowing methane to persist and eventually transform into diamonds rather than oxidizing to other compounds. The magnetic fields of Earth and Neptune, different as they are, might both be influenced by their different forms of carbon. Earth's magnetic field is generated by convection in our iron core, with carbon playing at most a minor role. But some scientists speculate that carbon in the core, perhaps in the form of iron carbide, might affect the dynamics of field generation. Neptune's magnetic field, tilted and offset as it is, might be influenced by the movement of diamonds through the conducting fluid of the interior. Both planets generate magnetism, but through different mechanisms potentially influenced by different forms of carbon. Life itself is the biggest difference between Earth and Neptune when it comes to carbon. Every living thing on Earth is built on carbon chemistry, from the simplest bacteria to the most complex mammals. We are carbon-based life forms living on a planet where carbon cycles through air, water, rock, and biology. Our existence depends on carbon remaining available in forms we can use, not locked away as diamonds or other inaccessible minerals. In a sense, Earth doesn't rain diamonds because it has something more, precious, a carbon cycle that supports life. This raises a fascinating question. Could life exist on a world where it does rain diamonds? Not on Neptune as it is, with its extreme conditions and lack of liquid water. But perhaps on a world with different conditions, where diamond formation was just one part of a more complex carbon cycle. Perhaps organisms could evolve that use diamonds for structure, the way Earth organisms use calcium carbonate for shells. Perhaps there could be a biology based on high-pressure chemistry, as alien to us as our water-based life would be to a creature from Neptune's depths. The comparison between Earth and Neptune also highlights how planetary mass shapes chemistry. Neptune is 17 times more massive than Earth, and this extra mass creates the pressure needed for diamond rain. If Earth were more massive, if it had accumulated more material during its formation, it too might have diamond rain. There might be a threshold mass above which planets naturally produce diamonds in their atmospheres, and below which they don't. Earth falls below this threshold. Neptune is above it. It's a reminder that planetary mass isn't just about size, it fundamentally determines what chemistry is possible. The evolutionary paths of Earth and Neptune diverged early in the solar system's history. Earth formed in the inner solar system, where it was warm enough for rocky materials to dominate, and where water could exist in all three phases. Neptune formed in the outer solar system, where ices could persist, and where it could accumulate vast amounts of hydrogen and helium. These different formation locations led to different compositions, which led to different internal structures, which led to different chemistry. The diamond rain on Neptune and its absence on Earth can be traced back to where each planet formed 4.5 billion years ago. But Earth and Neptune do share some surprising similarities, despite their different carbon chemistry. Both planets have weather, though of vastly different types. Both have circulation patterns driven by rotation and internal heat. Both have layers in their interiors, though the layers are made of different materials under different conditions. Both are dynamic worlds where materials transform and cycle, just through different processes. In a sense, diamond rain on Neptune is that planet's version of Earth's water cycle, a way for materials to move and change and create structure. The study of these two different worlds and their different relationships with carbon teaches us about planetary diversity. There's no single template for how planets work. Each world finds its own solutions to the problems of heat transport, chemical equilibrium, and structural stability. Earth solved these problems one way, with plate tectonics and life, and a water-mediated carbon cycle. Neptune solved them differently, with diamond rain and convecting ices, and a deep atmosphere chemistry we're only beginning to understand. Both solutions work, both have been stable for billions of years, but they couldn't be more different. This diversity extends to the thousands of exoplanets we've discovered orbiting other stars. Some are Earth-like, small and rocky with thin atmospheres. Others are Neptune-like, larger and ice-rich with deep atmospheres. Still others are unlike anything in our solar system. Hot Jupiters orbiting close to their stars, super-Earths with masses between Earth and Neptune, water worlds covered in global oceans. Each of these worlds likely has its own unique chemistry, its own way of handling carbon and other elements. Diamond rain might be common in the universe, or it might be relatively rare. We're just beginning to explore the vast space of possible planetary chemistries. The implications for astrobiology, the study of potential life in the universe, are profound. If planets can have such different carbon chemistry, what does that mean for the possibility of life? We know life as carbon-based chemistry in water, but that's just one possibility based on our single example. Could there be life based on different carbon chemistry, perhaps in the high-pressure environments where diamonds form? Could there be life based on entirely different elements, using silicon or sulfur instead of carbon? The diversity of planetary chemistry suggests the universe might have many different solutions to the problem of life, not just our familiar one. As we look to the future of planetary exploration, the contrast between Earth and Neptune helps define our questions and goals. For Earth, we seek to understand our planet's history, its climate, its capacity to support life. For Neptune, we seek to understand an alien chemistry, exotic weather, the behavior of matter under extreme conditions. Both quests expand our knowledge, but in different directions. Studying Earth teaches us about habitability and life. Studying Neptune teaches us about the extremes of planetary physics and chemistry. The technological challenges of studying these two worlds couldn't be more different. Earth we can explore directly, with drills and submarines and satellites. We can collect samples, conduct experiments in the field, observe processes as they happen. Neptune we can only study remotely, with telescopes and the data from a single flyby mission decades ago. We have to infer its internal structure from models, guess at its chemistry from laboratory experiments, imagine its diamond rain from theoretical calculations. The contrast highlights both the advantages of studying our home planet and the ingenuity required to understand distant worlds. Yet in some ways, Neptune's diamond rain is easier to understand than Earth's geology. The physics is simpler. Pressure transforms methane to diamond. The chemistry is cleaner. No biology to complicate things. No water to create complex reactions. The process is predictable. Given the conditions, diamonds must form. Earth's geology, by contrast, involves the complex interplay of life, water, atmosphere, and rocks over billions of years. Sometimes the alien is simpler than the familiar. The philosophical implications of these two different worlds and their different diamonds are worth contemplating. What is value when diamonds are as common as rain? What is rarity when the unusual here is ordinary there? What is beauty when it forms unseen in eternal darkness? Earth's diamonds are valuable because they're rare, beautiful because we can see them, meaningful because we've given them meaning. Neptune's diamonds have no value in human terms, no beauty without observers, no meaning beyond their physical existence. Yet they're the same substance, the same arrangement of carbon atoms. The difference is entirely in context and perspective. As our night journey continues, we find ourselves at the intersection of the known and the unknown, the familiar and the alien. Earth, the world we know intimately, the only world we've ever called home, doesn't rain diamonds because it's too small, too warm, too alive. Neptune, a world we barely know, a world we've glimpsed only briefly, rains diamonds because it's massive enough, cold enough, simple enough in its chemistry. The contrast illuminates both worlds, making us see Earth with fresh eyes and Neptune with informed imagination. The story of why Neptune rains diamonds and Earth doesn't is ultimately a story about the diversity of worlds, the universality of physical laws, and the endless creativity of nature in arranging matter and energy. It's a reminder that our earthly experience, precious and unique as it is, represents just one tiny sample of what's possible in the universe. There are other ways to organize carbon, other ways to create weather, other ways to be a planet. Neptune's diamond rain is just one example of these alternatives, beautiful in its strangeness, instructive in its difference. As we move toward the conclusion of our contemplation, toward the philosophical implications of diamond rain and our place in a universe of wonders, we carry with us this comparison between worlds. Earth, where carbon becomes life, and occasionally, through tremendous geological effort, diamonds. Neptune, where carbon becomes diamonds as naturally as water becomes ice. Two worlds, two solutions, both operating under the same physical laws but manifesting them in dramatically different ways. The universe, it seems, delights in variation, in finding multiple solutions to the same fundamental challenges. The question of future exploration brings our cosmic contemplation into sharp focus. As we lie here in the darkness, perhaps on the edge of sleep, we can imagine the missions that might one day unlock Neptune's secrets more fully. Picture a spacecraft, launched perhaps decades from now, carrying instruments we've only dreamed of. It would take years, perhaps a decade or more, to reach Neptune, a patient journey through the cold emptiness between worlds. But when it arrives, what wonders might it reveal? Imagine an orbiter circling Neptune for years, not just flying by in hours like Voyager 2. It could watch the storms develop and dissipate, track the seasonal changes we've only guessed at, map the magnetic field in exquisite detail. Perhaps it could drop probes into the atmosphere, armoured capsules designed to withstand pressures that would crush conventional spacecraft. These probes might not survive to the depths where diamonds form, but they could travel deeper than anything we've sent before, sampling the chemistry of the upper atmosphere, measuring temperature and pressure profiles, listening for the acoustic signatures of processes happening far below. The technology for such missions is advancing rapidly. New materials that could withstand extreme pressures, new instruments that could detect the signatures of diamond formation, new propulsion systems that could get spacecraft to Neptune faster than ever before. Some scientists have proposed using the diamond anvil cell technology that confirmed diamond rain in the laboratory as the basis for atmospheric probes that could survive Neptune's crushing depths. Others imagine swarms of tiny probes, each lasting only minutes but together painting a picture of the atmosphere's structure. But even without leaving Earth, our ability to study Neptune is improving dramatically. The James Webb Space Telescope is providing unprecedented views of Neptune in infrared light, revealing details of its atmosphere invisible to previous telescopes. Future ground-based telescopes with mirrors 30 meters across or more will be able to see Neptune with clarity approaching what spacecraft achieved from much closer distances. New techniques in computational modelling, powered by advancing supercomputers and artificial intelligence, are allowing us to simulate Neptune's interior in ever greater detail. These technological advances are revealing new mysteries even as they solve old ones. Recent observations have shown that Neptune's atmosphere is more variable than we thought, with storms appearing and disappearing, cloud bands shifting, the overall brightness of the planet changing over time. What drives these changes? How do they relate to the diamond rain happening below? Could changes in the rate of diamond formation affect the visible atmosphere? Each answer leads to new questions. Each discovery opens new frontiers of ignorance. The search for understanding Neptune's diamond rain has also led to unexpected discoveries closer to home. The same high-pressure experiments that confirmed diamond formation from methane have revealed new states of matter, new types of chemical bonds, new ways atoms can arrange themselves. These discoveries have applications in materials science, leading to stronger materials, better semiconductors, new technologies we're only beginning to imagine. The quest to understand an alien weather pattern has yielded practical benefits for human civilization. There's a beautiful circularity to this. We use diamonds, the hardest natural material we know, to create the pressure needed to understand how diamonds form on Neptune. We use the diamonds of Earth to study the diamonds of Neptune, and in doing so, we learn about both worlds. The diamond in a scientific instrument becomes a window into alien chemistry, a tool for understanding processes we'll never directly witness. Every diamond anvil cell experiment is a conversation between Earth's geology and Neptune's atmosphere, mediated by human curiosity. The cultural impact of discovering diamond rain on Neptune has been subtle but real. It's entered our collective imagination as one of those facts that makes the universe seem more wonderful and strange. Children learn about it in school, artists incorporate it into their work, writers use it as metaphor. It's become part of how we think about the cosmos, a reminder that reality often exceeds fiction in its creativity. The phrase diamond rain itself has a poetic quality that transcends its scientific meaning, evoking images of beauty and abundance in the cold darkness between worlds. But beyond the poetry, there's hard science still to be done. We need to understand the role of diamond rain in Neptune's energy budget more precisely. How much heat does it generate? How does this heat affect atmospheric circulation? We need to understand the chemistry better. What exactly happens to the hydrogen when methane breaks down? Does it form metallic hydrogen? Does it react with other compounds? We need to understand the dynamics better. How do diamonds move through the atmosphere? Do they create turbulence? Do they affect the formation of storms? These questions matter not just for understanding Neptune, but for understanding planets in general. As we discover more exoplanets, we need to understand the full range of possible planetary processes. Diamond rain might be happening on millions of worlds throughout the galaxy. Understanding it on Neptune helps us interpret observations of distant worlds we'll never visit. When we detect methane in an exoplanet's atmosphere, we can now ask, is it raining diamonds there? When we measure an exoplanet's heat output, we can wonder, how much comes from crystallization in the deep atmosphere? The philosophical implications of diamond rain extend to our understanding of complexity and emergence. How does simple chemistry, methane breaking down under pressure, lead to the complex dynamics of a planet's interior? How do countless tiny processes, each diamond forming and falling, add up to global effects on circulation and heat transport? Neptune's diamond rain is an example of emergence, where simple rules operating at small scales create complex patterns at large scales. It's a reminder that the universe builds complexity from simplicity, that grand phenomena often have humble origins. As we contemplate these vast scales and extreme conditions, it's natural to feel small. What are we? Brief biological fluctuations on a tiny rocky world, compared to the cosmic forces that create diamond rain on Neptune? But perhaps that's the wrong perspective. Yes, we're small and brief, but we're also the part of the universe that has become conscious, that can wonder about diamond rain on distant worlds. We're the universe's way of understanding itself, of appreciating its own creativity. In knowing about Neptune's diamonds, we participate in something larger than ourselves. The night deepens around us as we continue our contemplation. Perhaps you're already drifting towards sleep, carried by the rhythm of these words and the peace of cosmic perspective. There's something deeply calming about contemplating processes that operate on geological timescales, that have been happening for billions of years and will continue for billions more. Our daily worries seem less pressing when compared to diamonds falling through Neptune's atmosphere for eons, patient and eternal. Yet even as we find peace in these vast scales, we shouldn't lose sight of the wonder. It really does rain diamonds on Neptune. This isn't metaphor or poetry, but physical fact. Right now, as you listen to these words, as your breath deepens and your mind quiets, carbon atoms are crystallizing in Neptune's atmosphere and beginning their long fall through the darkness. They've been falling all day, all year, all century. They were falling when you were born, when humanity first looked at the stars, when life first emerged on Earth. They'll be falling long after we're gone, a cosmic process indifferent to human observation, but beautiful nonetheless. The beauty of Neptune's diamond rain isn't aesthetic in the conventional sense. We'll never see these diamonds sparkling in sunlight, never hold them in our hands, never admire their clarity or cut. Their beauty is conceptual, mathematical, the beauty of understanding how the universe works. It's the beauty of physical laws playing out on grand scales, of matter organizing itself into patterns, of simplicity giving rise to complexity. It's a beauty accessible only through science, but no less real for being abstract. This brings us to a deeper appreciation of what science gives us, not just knowledge, but wonder, not just facts, but meaning. In understanding why Neptune rains diamonds, we don't diminish the mystery, we deepen it. Each answer reveals new questions, each discovery opens new frontiers. The universe becomes not less magical, but more magical when we understand some of its mechanisms. The diamond rain is more wonderful because we know it's real, because we understand something of how it works, because we can connect it to the physics and chemistry we experience every day. The universality of physical laws that makes diamond rain possible also connects us to the cosmos in a fundamental way. The same forces that hold atoms together in our bodies create diamonds in Neptune's atmosphere. The same thermodynamics that governs our machines determines the stability of crystal structures under extreme pressure. We're not separate from the cosmic processes that create diamond rain. We're part of the same physical reality, governed by the same laws made of the same fundamental particles. In understanding Neptune, we understand something about ourselves and our place in the universe. As our journey through this cosmic mystery nears its end, let's return once more to the image that began our exploration: diamonds falling through an alien atmosphere. But now we see it with informed imagination. We understand something of the pressures involved, millions of times what we experience. We know about the temperatures, thousands of degrees in eternal darkness. We can picture the methane molecules breaking apart, the carbon atoms finding each other, the crystal lattice forming against all earthly intuition. The image is richer for our understanding, more wonderful for being grounded in science. The diamonds continue their fall, patient and eternal. Some might be tiny, barely more than clusters of carbon atoms. Others might have grown larger over time, accumulating layers like cosmic pearls. They fall through winds that rage at supersonic speeds, through chemistry we're only beginning to understand, toward destinations we can only imagine. Do they accumulate in vast layers? Do they dissolve back into the fluid interior? Do they transform into even more exotic forms of carbon? We don't know, and perhaps that's part of the beauty. Even with all our science, all our models and experiments, Neptune keeps its deepest secrets. The question that titled our journey, why Neptune rains diamonds and Earth doesn't, has led us through extremes of pressure and temperature, through planetary formation and evolution, through laboratory experiments and space missions. The answer, we've found, isn't simple but multifaceted, involving mass and composition, temperature and pressure, the presence or absence of life and water. Earth doesn't rain diamonds because it's a different kind of world, solving different problems in different ways, and perhaps that's for the best. A world that rained diamonds might be magnificent, but it couldn't support the kind of life that can wonder about diamond rain. In the end, the story of Neptune's diamond rain is a story about diversity and possibility, about the universe's endless creativity in arranging matter and energy. It's a reminder that what seems impossible from our limited perspective happens routinely elsewhere. It's an invitation to expand our imagination, to consider realities beyond our experience, to remain humble before the vastness and strangeness of existence. The diamonds of Neptune will never grace our jewelry or our technology, but they've already enriched our understanding and our sense of wonder. As you drift towards sleep, perhaps you'll dream of Neptune's diamonds. Perhaps you'll imagine yourself floating in that blue atmosphere, watching crystals form and fall around you. Perhaps you'll feel the peace of geological time, the patience of cosmic processes, the beauty of physics playing out on planetary scales. Or perhaps you'll simply rest in the knowledge that the universe is far stranger and more wonderful than we once imagined, that even now, in the outer darkness of our solar system, it's raining diamonds. The cosmic clock continues its patient ticking. Neptune continues its orbit, 1 year every 165 of hours, carrying its diamond rain through the darkness. The diamonds continue to fall, as they have for billions of years, as they will for billions more. And somewhere on a small rocky planet, orbiting an ordinary star, beings who evolved from carbon-based chemistry contemplate the diamonds they'll never see, finding in them a reflection of the universe's endless capacity for wonder. What if the greatest treasure isn't the diamonds themselves, but the knowledge that they exist? What if the real wealth is in understanding, even partially, the magnificent processes that create them? We may be small, temporary arrangements of atoms on a world that doesn't rain diamonds, but we have something perhaps even more precious, the ability to know about diamond rain on other worlds, to understand it through science, to find in it both humility and inspiration. The universe doesn't care about our wonder. Neptune's diamonds fall whether we know about them or not. But in knowing about them, in understanding them, in contemplating them as we drift towards sleep, we participate in something larger than ourselves. We become the universe contemplating itself, matter organized in such a way that it can think about other organizations of matter. We are the cosmos becoming conscious of its own creativity, and in that consciousness, perhaps, lies a beauty greater than all the diamonds of Neptune. As our contemplation draws to its close, we're left not with answers but with a deeper appreciation of questions. Why does the universe create such diversity of worlds? Why does carbon, the element of life on Earth, become diamonds in Neptune's sky? Why do we, brief biological fluctuations, care about processes we'll never witness, on worlds we'll never visit? These questions don't have simple answers, but in asking them, we touch something essential about what it means to be human, to be conscious, to be part of a universe that creates both life and diamond rain. The night is deep now, and perhaps you're already more asleep than awake, carried by the rhythm of words toward dreams. But before you go, consider one last thought. Every carbon atom in your body, every carbon atom that makes you alive and conscious and capable of wonder, could under different circumstances become a diamond falling through an alien sky. You're made of the same stuff as Neptune's diamond rain, arranged differently but fundamentally the same. In contemplating those distant diamonds, you're contemplating yourself, your own cosmic nature, your own participation in the universe's endless creativity. And so we return to where we began, but with deeper understanding. Neptune rains diamonds because it's massive enough to create the necessary pressure, cold enough to have methane, and simple enough in its chemistry for the transformation to proceed unimpeded. Earth doesn't rain diamonds because it's a different kind of world. one where carbon follows different paths, creates different wonders, enables different possibilities. Both worlds are magnificent in their own ways. Both are expressions of the universe's creativity. Both remind us that reality exceeds imagination in its capacity for wonder. The diamonds continue to fall through Neptune's eternal night. They fall without witness, without meaning beyond their physical existence, without any of the human associations we attach to diamonds. Yet in their falling, they tell a story about the universe, about the behavior of matter under extreme conditions, about the diversity of worlds and the processes that shape them. It's a story we've only recently learned to read, and we're still puzzling out many of the words. But what we've read so far fills us with wonder and anticipation for the chapters yet to come. Sleep approaches now like a gentle tide, carrying you away from conscious thought toward the deeper rhythms of dreams. Perhaps in your dreams you'll visit Neptune, see its blue atmosphere from above, watch storms larger than Earth spin through clouds of methane. Perhaps you'll descend into those clouds, feeling the pressure build, watching methane molecules dance and break apart, witnessing the birth of diamonds in the darkness. Or perhaps you'll simply rest in wordless wonder, your mind integrating all we've contemplated, finding its own understanding of diamond rain and distant worlds. Before you go, remember this. We live in a universe where it rains diamonds. Not everywhere, not on our familiar Earth, but out there in the cold reaches of our solar system and probably on countless worlds throughout the cosmos. This is the reality we inhabit, strange and wonderful beyond our ancestors' wildest dreams. We are part of this reality, made of star stuff, as Carl Sagan said, temporary arrangements of atoms that can contemplate other arrangements of atoms. In knowing about Neptune's diamond rain, we know something essential about our universe and our place within it. The story of diamond rain is far from complete. Future missions may reveal surprises we haven't imagined. New experiments may overturn our current understanding. Observations of exoplanets may show us variations on the theme we haven't conceived. Science is never finished, never complete, always reaching for deeper understanding. The diamonds falling through Neptune's atmosphere right now are falling through mysteries we haven't even formulated yet, questions we don't know how to ask. And that's perhaps the most wonderful thing of all. There's always more to discover, always more to wonder about. As consciousness fades towards sleep, as words dissolve into wordless peace, we're left with an image that will outlast our contemplation. Diamonds falling through darkness, patient and eternal, beautiful in their existence whether we know about them or not. They've been falling throughout our conversation, throughout your lifetime, throughout human history. They'll continue falling as you sleep, as you dream, as you wake to a new day on a world that doesn't rain diamonds but has something perhaps even more precious, the capacity for wonder. Good night, fellow traveller through cosmic mysteries. May your dreams be filled with the peaceful fall of distant diamonds, the patient processes of geological time, the vast scales of planetary existence. May you wake refreshed, carrying with you some sense of the universe's magnificence, its creativity, its endless capacity for surprise. And may you remember, in the midst of your earthly concerns, that somewhere in the darkness between worlds, it's raining diamonds, and that you, in your small and precious way, are part of the same cosmic story. The universe continues its patient unfolding. Stars burn their hydrogen into helium, planets orbit in their ancient paths, and on one small world, consciousness contemplates diamonds it will never see. On another world, far from the sun's warmth, carbon crystallizes in the darkness and falls like rain through an atmosphere no human will ever breathe. Both processes are part of the same reality, the same cosmic story, the same magnificent universe that creates both life and diamond rain, both consciousness and crystal, both the familiar Earth and the alien Neptune. And in the silence that follows these words, in the peace that comes with cosmic perspective, in the gentle approach of sleep and dreams, we find ourselves at home in this strange universe. We belong here, in a cosmos where diamonds rain from alien skies, where carbon can become both life and crystal, where understanding deepens wonder rather than diminishing it. The diamonds of Neptune, falling through eternal darkness, remind us that we live in a reality far stranger and more beautiful than we often realize, and that knowledge, that wonder, that cosmic perspective is perhaps the greatest treasure of all.